So thanks so much for the invitation to be here today. The title of my talk is Interfacing Spins with Photons for Quantum Simulation and Quantum Control. And so what do I mean by quantum simulation and quantum control? Well, roughly speaking, when I say quantum control, I'm thinking about the sort of effort to engineer useful entangled states. So there's a whole class of states that it's known if we could make them, they would be useful maybe for computation, maybe for precision measurements. They have names. You can draw pictures of them. On the flip side of that, entanglement comes in many forms. Another form of entanglement is what I might sort of very coarsely call useless entanglement, right? Sort of generic states of interacting many-body systems, okay? So this is kind of when today, the quantum simulation aspect of my talk will be thinking about entanglement in this form. And broadly, I'll try to convince you that cold atoms in an optical cavity, so cold atoms that can interact via photons, are a neat tool for being able to kind of study entanglement in both of these forms. And the sort of analogy I have in mind is if I were a painter and these tools, the cold atoms and light were my palette, there's more than one thing you might want to do. There are days when you want to paint something beautiful, useful. It's useful in the sense that you can sell it for a lot of money. But there are days when you might just want to drop some paint or some dye in the water and kind of see how it spreads. And maybe you'll learn something. Maybe it will also be beautiful.
And maybe those things get sold for a lot of money.
Right, exactly. And so these are kind of so these are two topics that I will hope to get to in my talk. So the outline is I'll start by sort of introducing an experimental setup for studying atom-light interactions and interactions mediated by light. And show kind of first experimental signals, but then a portion of my talk will also be theory kind of inspired by thinking about this setup in two directions. So the dropping the dye in the ocean, this is a section on scrambling quantum information. And then I will hope to have enough time to get to talking about painting a particular, or painting designer entangled states. So this is a new theory on a new scheme for quantum control. Okay, so let me start with some motivation that comes from this dropping a dye in the ocean picture. So the question is, this dropping some dye in the ocean, it's actually a metaphor for a question about quantum information. So the question is, if I have a qubit encoded locally in some many-body system, how fast can the information through interactions spread over all degrees of freedom? And the sort of inspiration for asking about this question, so this is called scrambling, originally comes actually from thinking about what happens to quantum information in black holes. Now, I'm not an expert in black holes, so I prefer to think about a little bit about qubits. Okay, but so there's an inspiration coming from thinking about black holes. And in that context, it's actually been shown or conjectured that there's a fundamental limit to how fast information can spread, which essentially, if there's some time scale for local observables to equilibrate, which is set by the temperature, the conjecture is that the fastest that the information can spread over the entire system is longer by something that's the entropy of the black hole, the log of the entropy of the black hole. Okay, so this is a conjectured limit. And to sort of get an intuition for where it comes from, I'm going to, because I'm more of a qubit person than a gravity person, I'm going to try to understand this, or try to give you an idea how to understand this in terms of thinking of the system of entropy S as a system of S qubits. Okay, so if you'd sort of like to make information spread very quickly in such a system, then a natural thing you might do if you're allowed only pairwise interactions that can happen on some timescale tau is to let each of these spins talk to a random partner in each time step, and then in each time step sort of reconnect them randomly again. And so information then can kind of double its extent in each of these time steps. And so the time for information to spread over the entire system would then be logarithmic in this number of qubits, okay? And so this, it certainly, if you were sort of less clever about how you connected things, it certainly could spread slower. But there's an argument that this should be the fastest possible.
But the tau interaction time is quite different from relaxation.
So the idea is that the tau is something that would be a time for if I have, locally, if I have some sort of gates that happen on the timescale tau, then I can already, just by sort of local interactions, have some dissipation on that timescale. But yeah.
That's different, right? Even in molecular kinetics, those are very different time scales. So which one are you referring to?
Can you repeat the question? Yeah.
Time
Yeah.
is very different from relaxation time of the whole system.
Good. Yeah. And so this is a time scale for a local observable to equilibrate. Yeah. And so exactly. And so generically, it will take much longer for the entire system to equilibrate. And you can think of this kind of scrambling, this spreading of information over the full system as some sort of very strong definition of thermalization. Yeah.
Is this relaxation time always related to temperature or the strength of the local interactions?
So either of these could come in. So in the sort of black hole case, there's only one time scale, which is set by the temperature. In sort of a generic quantum many-body system, you can imagine that the strength of interactions could come in, and the temperature could come in. The temperature might set a slower speed. At infinite temperature, I would imagine all that should matter is the time scale of the interactions. The temperature might set a lower limit, a limit that is lower than what you would get by thinking just about the interaction strength. Thank you. Okay, so I mentioned this as kind of, okay, so this is some intuition for what might set a limit to this scrambling. It gives an indication that the type of system one might look for if one hopes to see this in a sort of real physical system that one could build in the lab, is some form of non-local interaction, and probably also something very chaotic. So there are actually models that can be written down and are analytically tractable that exhibit this type of fast scrambling behavior. They don't look so easy to realize experimentally. So here's a model known as the Sachdev-Yekatayev model that involves non-local hopping of fermions, processes that look like this, involving pairwise correlated non-local hopping of fermions. There are some thoughts on how to implement this. The thought of making massive particles hop non-locally sounds daunting to me. So we started to think a little bit, though, about whether there might be kind of a natural approach to studying this type of physics involving having spin excitations that hop rather than massive particles. So the idea would be if one can generate models where I sort of map, say I have a system of spin half particles, and I think of spin down as some kind of a site with an unoccupied site, spin up as an occupied site, and I can engineer kind of flip-flop processes where a spin up and a spin down exchange their states, then this is a type of a hopping process. So this looks actually like a model of hardcore bosons, hardcore because two of them can't occupy the same site. But in contrast with massive particles, we might be able to actually use photons to generate a sort of non-local hopping of spin excitations. So the general idea of making non-local interactions with photons is not new. Cavity QED systems are an ideal tool for this. They've been applied sort of in one context, applying non-local interactions as a way of kind of generating entanglement on mass. So squeeze states, for example. Non-local interactions in cavity QED systems have been used in beautiful experiments realizing super solidity They've been envisioned as a potential tool for studying spin glass physics, not yet experimentally realized. So this is sort of a well-studied area that we started to think, well, maybe we can take this in a new direction of generating this kind of non-local hopping. So to be a little bit more concrete, how would you do this? The physical system you can have in mind is, so my spins will be two-level, in the simplest case, two-level atoms trapped in an optical resonator. And if you'd like to make the excitations hop, in other words, have this type of flip-flop interaction, then the type of scheme you can imagine is something like I drive the system with a control field, and an atom can absorb a photon from the control field, emit a photon into the cavity, thereby flipping its spin. Another atom could reabsorb that photon, emit it into the control field, flip its spin. This is a way of generating pairwise correlated spin flips. So, so the scheme would look something like this. This is my drive laser. This is the cavity mode. And what I need to do to make this a coherent interaction is I need some detuning so that the process where I put the photon into the cavity is just a virtual process. And in order for this process to be resonant, two spins need to participate. OK, so that's kind of the picture you can have in mind. In principle, this is very versatile, right? With spatial addressing, one could have controlled interactions between arbitrary regions of the system. The sign of the interaction is also something that one can flip by changing the sign of this detuning here, actually. So it could be a ferromagnetic, could be antiferromagnetic. And in principle, the interactions can be coherent. You might worry because there's light in the system and light can leak away. It can be coherent in the limit where this atom-like coupling strength is strong compared to the characteristic decay rates of photon leaving either through the mirror or through spontaneous emission. So if you want to kind of put all these put these requirements together of having spatial access to the system and coherent interactions, it actually forces you to kind of get into a tricky regime of cavity QED. Right, so you want essentially to confine light tightly. This figure of merit, the ratio of the atom-light interaction, G to the characteristic decay rates, cavity decay, and spontaneous emission, essentially scales inversely as the cross-sectional area of the mode. That's W squared. I didn't label it here. That's W squared. So you'd like to sort of get the best mirrors you can. You'd like to focus the light down tightly, but you don't want to make a very small cavity, or you won't be able to actually see what's going on or manipulate the interactions from the side. So we decided, we'd like an experimental setup where we can have strong coupling, but also optical access for imaging and addressing. And so that looks something like this. We said, let's have a situation where the light comes nearly to a point, but the mirrors are far away so that we can get at the atoms. So in practice, that means the setup is a 5 centimeter long optical resonator, but it's actually 5 centimeters minus 50 microns. If it were exactly 5 centimeters, the mode would come to a point in the center. We back off from that a little bit and have a waist with a waist of about 12 microns. And OK, the tricky thing is you can imagine if you tip or tilt one of these mirrors slightly, the mode will be misaligned. OK, so this is so in reality, this looks something like this, where these two mirrors are mounted in vacuum on some piezoelectric positioning stages that allow us to fine-tune the tip and tilt. And as one, and as well as the length, and as one kind of tunes the mirrors closer and closer to that concentric regime, at fixed mirror finesse, the cooperativity, which is this figure of merit interaction to decay ratio, goes up, and we can align it to a regime where that cooperativity is about 50. The best mirrors we ever measured looked like this could get up to 200 with a sort of current cavity lifetime of the current system, 50. So we're pretty happy with that. That means we can be in a regime of coherent photon-mediated interactions. This is what so that's the cavity itself. We trap atoms in a lattice in the cavity, and here's just a picture. It's sort of a spatially extended cloud. Right, you can get in through this large window right near the cavity, thanks to this near concentric geometry, and take pictures. Okay, a few hundred microns long. And okay, we can start to see that the spins are coupling to the cavity by the fact that we see the cavity resonance shift when the atoms are there, and we probe it with far detuned light. So here's a situation where we have atoms in one spin state, and it's shifted to the right, shifted the other way if we switch the state of the spins. So, okay, so we have some sort of spin-dependent coupling of the atoms to the cavity, and this will be the first ingredient to starting to make them interact.
How many atoms?
So, yeah. So in this particular picture, this is a few thousand atoms. And so now I have to be honest and say, in principle, we can get to this cooperativity of 50. Currently, things are not well optimized. So it turns out the atoms right now, we put them somewhere, and they're not in the center of the cavity, and there are various other factors working against us. We're not aligned at quite the smallest waist. So right now, we're actually working at a single atom cooperativity of about 1. And working with thousands of atoms so we can easily kind of image them. Eventually, we can push this to a regime of higher cooperativity and smaller numbers of atoms. But this is actually what we're currently doing. And so I mentioned the parameters for sort of prospects. And then, okay, so right now, that's the system, thousands of atoms, single atom cooperativity around 1. So strong single atom coupling and very strong collective coupling. Okay, so we said, we could push this and try to, optimize the atom-light interaction strength, but we'd rather start playing and kind of, see what the atoms do. So let me say a little bit about what one might expect. So there are a few things that one can think about in the context of this type of flip-flop interaction mediated by the cavity. There's a very simple limit where if I simply put the atoms in the cavity and let them all interact collectively with the cavity mode, so no local addressing, if I initialize them all in the same state, then I can sort of simplify this actually to a collective spin picture, where if I do a little bit of algebra, I can show that I can sort of rewrite this Hamiltonian as something that just looks actually identical to a situation where one has Ising interactions. So in some simple limit, it might even not matter whether the form of interaction is S plus or S minus or SZ, SZ. Okay, so this is a model that's well studied. It gives rise to a so-called twisting dynamics. This should say SZ, I apologize. Right? It's well studied because it gives rise to squeezed spin states. And so these types of interactions, we've previously realized them in cavity QED systems. They've been studied in Bose-Einstein condensates by collisional interactions. And there are ion trap experiments realizing similar interactions via the Sorensen-Molmer type of gate. So yeah. And the sign can be controlled so there's a laser frequency that can control the sign. Okay, so this regime of kind of global spin-spin interactions is quite well studied. From my perspective, what sort of is interesting about the cavity QED system compared, for example, to a Bose-Einstein condensate that would have this that same form of interaction in the case where I initialize the system in a permutation symmetric state of the spins. What's interesting about the cavity QED system, though, is that the interaction doesn't have to be global in this and have this simple form, right? So that opens actually a number of different directions. As soon as the couplings to the cavity mode are non-uniform, it turns out that the Hamiltonian one gets is one that actually maps onto an NP-hard problem. I don't claim that I know how to solve it, but that's sort of an indication that there's some richness there. Okay, in principle, the cavity gives a way of sort of coupling, for example, one-to-many. I'll come back to that a little bit later. Okay, but maybe if one can make some more interesting non-local interactions beyond, that go beyond this collective spin physics, that could also be an ingredient for studying this type of fast scrambling that I showed before. So to get to something that's beyond something I can describe in terms of a sort of single collective spin of the ensemble, I need to do not only collective measurements, this is in some sense a collective measurement of the total spin of all the atoms, but I also need some kind of a local measurements. And so the ingredient that we said that we need to add to our toolbox is state-sensitive imaging. So I'll show a few pictures along these lines, so let me show what I'm doing. So each line in this picture is essentially, you can think of it as a 1D picture of the cloud, okay? So the system is sort of roughly one-dimensional. I integrate over the transverse direction, and this is essentially the population difference between two hyperfine states. And in this is actually sort of a simple example where all I've done is put the atoms in the magnetic field gradient, and the vertical direction in this case is just the basis in which we measure in the spin. So it's effectively, this is an image of sort of Ramsey spectroscopy in a magnetic field gradient. So just to kind of illustrate the imaging capability, and okay, if one lets this evolve as a function of time, one sees finer and finer fringes. And okay, so that's just one example that we can image the spins, and in principle, we can image them in any basis. Okay, so we want to actually, yeah. Mm-hmm.
So I'm still missing what is x and what is phi.
Sorry, yes. So let me be clear. So okay, each row is a 1D picture of the cloud, state sensitive. The different rows are just.
Does that correspond to up there, or does it correspond to anything?
So this direction up here is the horizontal direction in the image.
Okay.
Thank you. Yeah. And in this particular case, the sequence is really just Ramsey spectroscopy. The phi is the phase of the second pi/2 pulse. So it's just a way of sort of testing that we can image the spins in any basis, kind of. Okay, so that's a good tool for being able to see what's going on, and we'd like to, put this to use to look at interactions. So okay, so let me say a little bit more about an experimental scheme for implementing these kind of flip-flop interactions. So I said before, the basic idea is a 4-photon Raman process that generates pairwise spin flips. And so I can describe this again in this kind of picture where I'll think of sort of an occupied site as this spin-up state. I'll have that be this solid red circle. Unoccupied site will be the empty red circle. And okay, so this is, I can think of this then as the excitation hopping, in this case from the right to the left, right? So to do that, I'd like to have a drive laser that is detuned from cavity resonance by an amount that's the Zeeman splitting, if these are two Zeeman states, minus some detuning little delta, which I'll call the 2-photon detuning, right? So if little delta were 0, then there would be a resonant process that flips a single spin. Making little delta non-zero gives a non-resonant process that should then allow this 4-photon process to dominate. So that's the basic picture for spin 1/2. Actually, in rubidium, it's a little bit more complicated. In a modest magnetic field, we have 3 states that are all coupled to each other. So it'll actually be, it's a spin 1 system. Okay, so now I can actually think of kind of each atom as sort of a site that has 0, 1, or 2 spin excitations. So the different MF quantum numbers in rubidium, I'm thinking of as different numbers of spin excitations, right? And so now they're actually, the Hamiltonian that one gets still looks essentially as it's just a sum of these flip-flop processes, but there are various processes you could imagine happening, right? I could have a single excitation in one atom, none in another, and have that excitation exchange sites. Or I could have, for example, 2 atoms, each with a single excitation, and turn that into 1 with 2 and 1 with 0. Incidentally, this is actually kind of similar to dynamics that are studied in spin 1 Bose-Einstein condensates. So, okay, so those are the types of processes you might expect to occur. And on top of that, though, if we're not careful about this 2-photon detuning, dissipation is another thing we might need to think about, right? That would just be losing spin excitations but via this resonant Raman process. So we'd like to see whether we can observe these processes. An important note to keep in mind is how does the interaction scale compared to the dissipation? Well, as long as one detunes far from cavity resonance, this ratio, this interaction to dissipation ratio can be large, scaling with that detuning. So to sort of start to see whether this works, the experiment we can do is initialize all atoms in the doubly excited state. particular Zeeman level. And then locally make a region where we have fewer spin excitations, okay? So apply a Raman pi/2 pulse in some region of the cloud. And now the question is whether we can see excitations from this fully excited region hop into the region where we've sort of depleted the spin excitations. So to do this, we can turn on this drive field at some variable 2-photon detuning and, well, see what happens. Okay. So first, let me consider a simple case. If I just set the 2-photon detuning to 0, then I expect, well, this dissipative process to be resonant, right? And I will just expect all of my spin excitations to leave through this Raman process. This is essentially a super radiant decay process that I expect to happen. And so we can we try that. So here's the data. I should say this is just each row here is really a single shot of the experiment where we, again, it's a 1D image of the atomic cloud. The different rows are different times after we turned on that drive field. We start out with, this is the region where we applied the Raman pulse. So we've kind of have a reduced excitation in this region. So the blue cut are these data. So essentially fully excited at the edges, reduced excitation in the middle. Okay, and you just see, as you would expect, that the spin excitations decay. One can look at this versus atom number. It displays a super radiant scaling. And okay, so this is the dissipative process that is not what we're aiming for. Questions about what that's showing so far? Yeah.
So
yeah.
It looks like already at time 0,
yeah.
You've got depletion. So is time 0 not?
In this central region? In the central region.
Yeah, in the central region.
Yeah, so again, so we did that on purpose. This was a Raman pi/2 pulse that intentionally depletes the central region. What we'd like to see is that if we go away from this resonant case, that we can start to see some excitations hop into that central region from the edges.
Give the pulse,
yeah.
And then after the pulse is over, this is the evolution.
That's exactly right. Yeah. Okay. And so, okay, so you can see a few things. You can see that you see this expected decay. You can also see we have some technical noise, so we're ironing that out. That's some of these stripes. Another thing you can see is actually the decay happens faster on the right side of the cloud than on the left. There are atoms all the way out here. They're much, much slower to decay. This has to do with the fact that the atoms, as I said, are not at the center of the cavity, and there's actually a gradient in the atom-like coupling strength across the system. So, okay. So then we said, let's detune. And so this is very preliminary, but we go out to a detuning, let's say, of 5 cavity line widths. And so just to, I should say this is data from last week, so don't. But okay, so we go out to a detuning of 5 cavity line widths, and we see something very different. So we were excited when we saw this, because now if I look, this central region, that's the blue line, this is where we initially sort of depleted the spin excitations. And rather than seeing this decay, we see the population of spin excitations go up, right? So this is becoming redder. And we start to see the spin excitations appearing in this other region of the cloud. So that's the green going down. Sorry, we start to see the spin excitations hopping from this right region of the cloud into the center, right? Okay, so you can sort of, this is I say very rough simulation because, well, all very recent, but just to sort of see that at least sort of qualitatively, this kind of matches the behavior we would expect, taking into account some non-idealities like the inhomogeneous broadening of the atom-like coupling. Okay, so we're seeing these oscillations, and this is a really exciting first step in being able to use light to controllably make these excitations hop over long distances, right? This is hundreds of microns. So, okay, I can even roughly try, again, very rough model to see whether I can capture the larger picture. And this sort of hopping of the excitations from this region into the center, right? If I look at kind of these 3 blobs of where the depletion is, reasonably well matches what we're seeing in the experiment, taking into account that the atom-light coupling is stronger on this side. So this is, again, this is very early data. We're working on controlling lots of things better to make these interactions more and more coherent, the homogeneity of the atom-light interactions, cavity stability. And in principle, we can go to even larger 2-photon detuning to get more into the coherent and away from the dissipative regime. And that's also just a technical improvement. So all of these things are on the agenda. In terms of sort of fundamental limits, at the end of the day, the cooperativity is sort of the key figure of merit for deciding how coherent these interactions can be. And that's because, well, I need to detune from that, detune to get away from that super radiant process. So I would like to send my light in further and further from cavity resonance. I need to send in more and more light. That means that eventually I'll run into a limit where that strong drive field causes spontaneous emission. And so there's some happy medium where this is kind of optimized, which scales with cooperativity. And so roughly speaking, the big picture is that at large collective cooperativity, one can study coherent, we should be able to see very coherent collective dynamics in this system. So that's something that we're already well equipped to do. And by really using our cavity at its optimum, we can also be in a regime of very high single atom cooperativity where one can think about realizing really coherent pairwise interactions, envisioning having a small array of atoms interacting via the light field and studying those at the single atom level. So, okay, those are different directions one can hope to go in this system. I think this idea that there's this kind of cooperativity setting a figure of merit for how coherent the interactions can be. It's kind of, it raises a broader point that I always think of photons as a very sort of a precious resource, right? I'd like to use them as efficiently as I can because there's always some small chance, small if we work hard, that they will leave. So I think that sort of raises the broader question of kind of how efficiently can we use light to spread information in a many-body system. And so it kind of raises the question also, can we get some insight into this from that fast scrambling conjecture about, and in particular, can we learn something by trying to engineer fast scramblers with this non-local hopping? Okay, so that actually allows me to transition into the second part of my talk, which is about scrambling quantum information. And in particular, I want to say a little bit more about how one quantifies this process of scrambling and some prospects for interesting non-local models that we might hope to study. As I'm transitioning, maybe I'll ask first, are there questions about this first part? Yeah.
That's a basic question. So you're using the term non-local. It sounds like non-nearest neighbor interaction would be a better title for that. Do you mean something different than just non-nearest neighbor interaction?
Well, yeah, so non-nearest, so yes, I do actually. So you could have second neighbor interactions. So for example, Chris, who's sitting in the front row, has done really beautiful experiments controlling power law interactions in ion traps. And so those are not nearest neighbor interactions. And there's a sort of tunability of how local or non-local they are in some sense. But they're strongest for ions that are closest to each other, and then the interaction strength falls away. So
by non-local,
yeah.
Typically, like first, collapse of wave function, could be infinitely far away.
So
this is sort of mediated by.
And so in some sense, everything is local. All interactions are local. All interactions are local. And the closest thing we can come to having something that is sort of different from that is, well, if we have photons convey the information, photons travel at the speed of light, to the extent that I can express what happens at the end as a spin model, the photons give a way of effectively having, in one example, interactions that are equally strong across an entire system, or maybe that are even stronger for spins that are further away. And so that can, so I'll touch on that in a moment. Okay, so good. So let's say one wants to actually ask about these, fundamental limits in scrambling, how fast information can spread. The first question is kind of, how should one actually quantify that? And so, we are sort of classical intuitions of chaos as being something about diverging trajectories in phase space. Doesn't really work in a quantum system. The overlap between quantum states is conserved. So still, though, there's a way of formalizing kind of the notion of a butterfly effect. And that is to think about how commutators grow in a quantum mechanical system. So this is sort of an inherently quantum mechanical version of a butterfly effect. So the question you can ask is, I have some many-body system, and I can think about maybe a spin that I rotate here, and if I'd like to know whether the effect of that has propagated elsewhere in the system, say to here, a question you can ask is, does this local spin rotation v commute with the local spin rotation w? At equal times, these operators commute. But if I think about the Heisenberg operator here at a later time, it might fail to commute due to the fact that, well, there are interactions in the intervening time in this system. So actually asking about how this Heisenberg operator, where H is the many-body Hamiltonian, whether this commutes with this operator V, or how large the commutator is some measure of to what extent information has kind of spread across the system. Okay, so this kind of quantum mechanical butterfly effect is one other way to sort of express it. This sounds a little bit jargony. It's sometimes referred to as an out-of-time order correlation function. But really, it's just so this sort of looks fancy. It's asking about some overlap of overlap of two quantum states. This is, I think, the easiest way to think about this. So I can ask, what is the overlap between the quantum states that would be prepared by applying the operator v at some time and w at some later time? Or on the flip side of that, applying the operator w at the late time. So what does that mean? So let the system evolve, apply this some spin rotation w, and then going back in time and applying v. So asking about how those quantum states compare is the same as asking about the commutator between these operators. And so another way to kind of think about this is you can think of this as sort of forming an interferometer, where the upper branch of the interferometer is one where everything happened in the right order in time. Like I gave all of the slides in my talk in the correct order. This one would be one where I actually skipped an important slide at the beginning and then had to flip all the way back to that crucial slide to sort of fill in the picture. And if I wait a very long time before doing that, then you might be very confused. And so this is sort of like measuring the overlap between the happy you and the confused you. Okay, so if you want to do this, there are a couple of tools that you need. You need some way of switching the sign of your Hamiltonian. You need some way of measuring the overlap between many-body quantum states. And it's actually this idea of time reversal is actually, I have to say, how I first sort of started to learn about this whole question of scrambling. So it all started with an email from Brian Swingle, who's in the audience, who had the wonderful subject, question about reversing time. Okay, so it turns out we had been thinking about time reversal in a very different context, which is, so one reason to think about this, what Brian had in mind is sort of a classic approach to diagnosing chaos, which has to do with sort of perturbing a system and seeing whether you can bring it back to its initial state. We had actually been thinking about a flip side of this, which is asking whether you can use this question of, does the system come back to its initial state after a perturbation, as a way of sensing perturbations. So it turns out, actually, if you kind of apply this kind of echo concept of going forward and back in time with some small perturbation in between, in this type of a Hamiltonian that I showed before, it actually turns out to be a very valuable tool for sensing near the Heisenberg limit in a way that's very robust to detection noise. So I'm not going to say more about this, but this is actually how I first started talking with Brian about schemes for reversing time. And it turns out that very soon thereafter, there was a beautiful experiment in the group of John Bollinger and Anna Maria Ray using precisely sort of such an echo scheme, just a little bit more sophisticated, and also using exactly this kind of twisting interaction I showed before, to illustrate, to perform a measurement of this out-of-time order correlation function, in this case in a trapped ion system. So without going into too much detail, I'll say this is a scheme that basically just involves the ability to have a Hamiltonian that one can evolve forward and backward in time. So switching the sign of a detuning, of a laser detuning, for example. And it works for simple initial states with only requiring sort of measurements of the total magnetization of a system. Sort of as if you want to think about measuring these commutators in very generic many-body states, there are more sophisticated schemes, and Brian is the expert on this, and he's in the audience. So you can ask him, and I won't go into too much detail on this. Suffice it to say, there are now methods of measuring the growth of these commutators applicable in a wide variety of many-body systems. And the question you might ask, though, is actually what does one expect to measure, and what signatures should one look for in a chaotic system? So I have a couple of examples of this, and actually, in the interest of time, I'm not going to give both. So one system that is well studied is kind of a chaotic collective spin model known as the kicked top. And all I'm going to say about this is that there's a beautiful experiment that's actually been done that's the first measurement of the out-of-time order correlation functions in a kicked top system. This has been measured now applying the scheme that we proposed with Brian in Bose-Einstein condensates. So this is kind of a neat realization of a collective spin model where the spin states are momentum states of a BEC. Okay, so this many-body chaos as diagnosed by the growth of commutators is something that can now be measured in a variety of experimental systems. This is an example, and the demonstration for a twisting Hamiltonian I showed you before. These are examples studying kind of collective spin models, which in the cavity QED setting, you could realize with these kind of all-to-all interactions. But something that we've been thinking about is kind of, can one engineer, using light, more complex non-local interactions that sort of yield richer many-body physics than thinking about a single large collective spin? So I showed you before that if all atoms interact uniformly with the cavity, there's sort of, if they're initialized in a symmetric state, I can think of everything as being the physics of a single collective spin variable. If they're initialized in a non-symmetric state, which was this sort of hopping I showed you earlier, you can get a little bit richer physics. But still, this sort of all-to-all interaction is not well suited to sort of exploring all of a large many-body Hilbert space. So there's an intriguing direction that we would like to explore, which is getting more versatile control of the hopping in this type of the hopping of spin excitations. And the dream would be to have some sort of arbitrary control of the hopping as a function of distance, so that nearest neighbors could be interacting most strongly, but perhaps also very distant neighbors could be interacting most strongly. And it turns out, actually, there's a very elegant scheme for doing this, which draws inspiration from optical lattice experiments, where one can control the hopping between nearest neighbors in the lattice via a Raman coupling. So the idea is if I tilt an optical lattice, then the hopping goes off resonance, but one can restore the hopping with a two-photon coupling and do things like control the strength or the phase of the hopping. So this has been used to make artificial gauge fields. Well, in a similar way in the cavity, if one applies a magnetic field gradient, then that would suppress this type of all-to-all hopping that is engineered by applying a single control field. But we now have a situation where the resonance condition actually depends on the distance between the spins. And so this is in principle a way that just by sort of having a modulated control field with various frequencies, we could dial in the dependence of this hopping matrix element on the distance.
Sorry.
Yeah.
Can I ask you the setup? Do you have atoms in an array, or you just have three-dimensional atom assembly? It's quite different in those cases.
So our atoms are trapped in a lattice. Right now, they're just sort of randomly filled into the lattice.
Right. So you don't have or and or, right?
Sorry?
You don't have or and or, the first case that you indicated.
All-to-all interaction.
That's what you used a slide ago. Or and or gives you a single particle, right? And you are interested in non-local, so it could only be very far away hopping that could give you non-local.
So in the simplest case, we get a situation where, to the extent that if the atoms are uniformly coupled to the cavity mode, then, and then they weren't quite uniformly coupled, but if they're uniformly coupled to the cavity mode, then each spin interacts equally with any other. And so a spin excitation in one place is equally likely to hop anywhere in the cavity mode.
Is that true? That
To the
you can have many different distance hopping with equal probability? I doubt that.
yes.
It's equal probability.
So again, within the regime where the intensity of the cavity mode that's mediating the hopping is constant, the probability of a spin in one place to interact with a spin in another place is independent of the distance. Within that range, of course, the cavity mode itself has a spatial profile. If the atoms are at very low intensity, they will couple less strongly. But the sort of key point is there's a single mode of light that mediates the interactions. And so naively, that sort of limits the complexity of the interactions that one can expect to see.
So all those lines have equal probability. Is that what you're saying?
And so maybe I can go back. So this is sort of what's most natural to realize, this type of interaction structure in a single mode cavity.
And you can have all-to-all.
Is all-to-all. That's actually the most natural thing to realize. And the real mechanism, it's a one-to-all coupling. All of the spins couple to a single mode, and that single mode couples again to all of the spins. And the net effect is effectively an all-to-all coupling.
Even if it's on an array.
Even if it's on an array, if the size of the array is small compared to the range over which the intensity of the mode changes.
Yeah, there's several conditions that need to be.
So there are several conditions. So exactly.
Even if it's not
So-
in an array, right? I mean, it's,
That's right, yeah. So it's sort of, there's no sense of distance in kind of the simplest case where I have a single mode and its intensity is constant. And so the question is kind of, can one put in a sense of distance and then control how the interactions depend on distance? Okay. And so to put in that sense of distance, a direction we can take this is apply a magnetic field gradient. Now the condition for this interaction to occur, for this resonant four-photon process to occur, depends on the distance between the spins. And so in general, by controlling the frequencies of light that one sends into the cavity, one expects to have control over the distance dependence of the spin-spin interactions. And there's actually kind of a very cute realization you could come to, which is that at the end of the day, it's some laser with which you would like to drive the cavity, which is phase modulated to generate multiple frequencies. And the profile of the phase modulation should end up dictating actually the dispersion relation for these spin excitations that I'm thinking of particles as particles hopping in the cavity. So you could imagine playing a lot of games with this. So like, I'd like to efficiently spread information over long distances with sort of a modest number of control fields. So maybe you'd like to have a situation where each spin can talk to its first neighbor, its second neighbor, its fourth neighbor, its eighth neighbor. So something very exotic that you would not get in nature. You could imagine these being individual spins or some sub-ensembles in an extended cloud. But roughly speaking, if you think about it at the end of the day, what this means is, well, the nearest neighbor hopping is would give some sort of cosine dispersion relation. The longer and longer range hopping would give sort of additional wiggles in the dispersion relation. And at the end of the day, you add it all up, and the dispersion relation would be a fractal. So not something that naturally appears in nature, but something we might hope to engineer in the lab. OK. So that kind of looks sort of crazy. And you might ask, is this something one can use to study many-body chaos? And well, the answer is, in principle, this is actually still an integrable model. But if one way to see that is actually knowing that there's a conserved quantity, which is the quasi-momentum. Another way is to look at a standard diagnostic of chaos, which is looking at statistics of the energy levels, of the spacings between nearest neighbor energy levels. Okay, this is not yet a chaotic system, but it turns out that sort of this type of model combined with disorder is chaotic. And again, one way to see it is by looking at the histogram of the energy level spacings. There's a repulsion of nearest neighbor energy levels, which is a signature of chaos. And one can sort of think about this model. The reason I like this model is one can think about it in different regimes. So you could ask about single particle physics. That's the regime where I don't have many spin excitations. I'm just showing some results from just exactly diagonalizing a small system of 9 sites. So if I just have a single excitation, that's just a single particle hopping. If I have sort of half the sites excited, then it's actually sort of a strongly interacting type of a model. And then you can ask sort of, how chaotic is the system in different regimes? And looking at sort of histograms of the energy level spacings don't tell you much about this. So the question is, can you sort of, are these out-of-time order correlation functions maybe a way of seeing more about how fast the model scrambles? How deeply it scrambles. Is it equally chaotic, whether I have a single particle or many? And do interactions play a role? And so just sort of to start to explore theoretically the types of physics one could see in these non-local models, we asked, how does one of these out-of-time order correlation functions behave as a function of the number of spin excitations that you put in the model? And there's actually an interesting behavior where one sees it decay further and further as one approaches the regime where you have half filling and the system is the most strongly interacting. You can actually ask how far does it decay, and the furthest it could possibly decay is set by sort of the dimension of the Hilbert space, and in the what I call the strongly interacting limit, where the system starts with half the sites excited, it decays to that lowest possible level, which is to say the kind of Heisenberg operators describing local spin rotations start to look like random matrices after some evolution time. But only in the case actually where this model has is sort of half filled with spin excitations. And so there's sort of an indication that this is a type of system where interactions actually play a role in promoting scrambling. And so there's some interesting many-body physics here. Okay, so this is something that I found interesting theoretically from thinking about the properties of this model. It's not something that realistically I expect to be able to measure in an experiment, a correlation function that is exponentially small in the system size. But what might be more realistic is asking something about how commutators grow at short times. And so just kind of for illustration, if one asks about a local model, right, the type of behavior one would expect to see, and this is actually just a numerical simulation of a local but chaotic model, is something where this commutator is very nearly 0 up until some time that is depends simply on the distance between the spins, right? There's kind of a light cone type behavior that one expects to see for the onset of an influence of an operation performed on some spin I on a different spin j, right? By contrast, for this kind of non-local model I showed you before with this logarithmic structure of couplings, roughly one expects the time for a signal to propagate to depend on kind of the log of the distance between the two spins. And well, it's hard to say exactly, is this a logarithmic behavior in numerical simulations and small system sizes? But certainly one sees something very different from this kind of a light cone, right? And so, we're on the one hand intrigued by trying to theoretically understand these types of non-local models better, but at the end of the day, to ask something about, is there a logarithmic scaling versus a linear one, maybe we need quantum simulations. So, yeah. Yeah.
So presumably you can control the non-local on the right while the HI is at the field.
So this is some disorder to make the model chaotic. And then the control of how non-local it is is, so I didn't actually, perhaps I should have explained this a little more carefully, but the control of how non-local it is. In this particular case, I've just chosen this kind of model where I let spins interact with first, second, fourth, and yeah,
In principle, you have two
eighth
ways
neighbor.
to control it, right? From the local and the non-local, right? And then the integrable versus chaotic.
Yes, these are two different knobs, right? And so, yeah, that's right. These are two different knobs, and the point is, if it's chaotic but local, there will still be some kind of delay for information, or time for information to propagate that just scales as the system size. So one expects kind of to see a linear dependence of the time before one sees any effect on this commutator. Sorry? It goes smoothly. So there's an interesting question of sort of what happens kind of in between, or as one tunes, are short-range interactions stronger than long-range interactions? Are long-range interactions stronger than short-range interactions? So it turns out, actually, I recently wound up in a conversation with a string theorist who told me that if one takes this model and makes the long-range interactions stronger, one arises at a totally different notion of geometry, which is a non-Archimedean geometry. That's a story for another day. But but I think it's sort of interesting to think of having a physical system where one can kind of tune those knobs and what new physics. Yeah.
Sorry.
Yeah.
Go ahead.
Yeah.
You said the local interaction is still chaotic. So the fact that the light cone is linear, this is totally different from the exponential divergence, like in a Lyapunov exponent.
So there's a second question you can ask, which is after this delay, how fast does the correlation decay? So there's sort of a time that's linear in the system size. Yeah.
The initial
Yeah.
line, and whether it's polynomial or logarithmic, you're saying it doesn't matter. They're all chaotic. Is that true? It seems like.
I'm not sure I understood the question. Sorry. Yeah.
So you said both the linear and logarithmic are chaotic. Is that?
In this particular case, these are both chaotic models, but I put this here just as sort of an illustration that, if one has a system with local interactions, one expects to see a scaling that's linear in the system size before there's.
Enough, I guess to rephrase.
Yeah.
Is that enough to define chaos, that the light cone is linear?
No. I don't think so. So, sorry, you're asking.
So this
Yeah.
is a chaotic system, but the linear light cone tells me that there's no chaos, or?
No. So the claim is, even if I have a chaotic system, but with, let's say, so simple case would be something like, Ising model in a transverse and longitudinal field with nearest neighbor interactions. That system is chaotic. It's not integrable. But
that
yeah.
shows up in the linear light cone.
Yeah. Yeah.
Maybe let her finish her
Yeah.
thought. because
Yeah, I've already
it's
run a bit.
done.
Yeah.
So,
So okay.
Monika will be around and she will.
Yeah, so, yeah.
So,
Okay, so the main point here, yeah, there's a sort of, yeah, so maybe we can discuss this later because I don't quite. Okay, so. Okay, so we're excited about exploring the possibility of kind of versatile engineering of interaction graphs in the cavity QED system. I showed you sort of first experimental progress on starting to see this non-local hopping of spin excitations. There's lots of work to do to make it more coherent and more controlled, but I think there are very exciting prospects with the system. Okay. And then you can dream of, can we realize black hole analogs in the lab, or does this teach us something about efficient ways of generating maybe also useful entanglement? So I really wanted to say one more thing about useful entanglement, but I think maybe I'm out of time. So I guess that's the question. Do I get 5 minutes to say something about useful entanglement, or should we? Yeah?
we'll be faced with angry, hungry people.
I'll be faced with angry, hungry people.
Well, please.
Yeah, so, okay. So what was this about painting that I said at the beginning of the talk? So for the people who prefer kind of well-controlled generation of entanglement, I wanted to say one thing about actually, a lot of the original motivation of the experiment was thinking about can we use photons to engineer specific entangled states? So one thing you could dream of is using a single photon interacting with an ensemble to make some kind of superposition states, macroscopic superposition states of the state of a small ensemble. The challenge in sort of anything using photons is always dissipation. And so we sort of thought, okay, really, one should take, ideally, maybe even a twofold approach. So we've worked hard to get a system where we can have a large interaction to decay ratio. Once things are well optimized, this should be about 50. But at the same time, we were thinking, can we also kind of get a second win by devising entanglement schemes that are robust to photon loss? Okay, so I'll just actually cut to the chase because I'm low on time. So the idea is the following. Let's say a natural interaction to get in this cavity QED system is a dispersive interaction where let's say I have a single photon in the cavity, and the mode is detuned from some excited state so that I have basically a light shift on this spin-up state if there's a photon in the cavity, and no light shift if there's no photon in the cavity. So that looks something like this. What it means is that if there's a photon in the cavity, the spins precess, and by some amount, that's the light shift times the time. So the question you can ask is, suppose that I send onto the cavity a weak field that contains at most one photon. Well, in that case, if I detect the photon at a time t later than I sent it in, I send it in a short pulse, then I know exactly how far the spins precess. So now you can ask the question, if I send this weak field in 2 pulses, so spins start out like this, at some later time I detect a photon, there's going to be some ambiguity in how much time the photon spent in the cavity. It could have spent the time a short time, or it could have spent a longer time, depending whether it went in the first or the second pulse. So the question is, does this give rise to a Schrodinger cat state? Who thinks it does? A few people nervously raised. Who thinks it doesn't?
It depends what you mean by a cat state.
Okay, let's define a cat state as a coherent superposition of the spin pointing in these 2 directions. Let's define it as an equal superposition. Okay, so yeah, who thinks it doesn't? Why?
Well, I think that maybe there's a good chance that an atom will scatter a photon out the side, and that could be a bad thing.
Okay, yeah, so you might lose the photon, that's one thing. But let's say I have a very good single photon detector, and I'll just ignore my attempt if I lost it, and then I'll try again.
Oh,
So maybe I can win something by making this a heralded scheme. How fast is my detector? Okay, that might come in, yeah.
Anyway, I'm going to
So-
say yes.
yeah.
It's a superposition. Whether it's equal, I have no idea.
But actually, it seems like maybe it shouldn't. What if this time is longer than the cavity lifetime? Then it's very unlikely that the photon will actually have gone in the first pulse. It probably went in the second pulse. So the cute thing that we realize is actually, if you imagine doing the same thing, but you make the second pulse weaker than the first pulse, then actually one can have a situation where I really don't know which pulse the photon came in. And I, in fact, should get an equal superposition of the spin pointing in 2 orientations. So I kind of think this is what the painting I referred to at the beginning of the talk. I sort of think of this as using a photon as a paintbrush. Each pulse is sort of puts a blob of quasi-probability for the spin to be oriented in a particular direction. And the key thing is that in applying this paintbrush, one needs to shape the pulse in a way that takes into account the cavity lifetime. So then you can also imagine about making other states. If I wanted to make a ring on the Bloch sphere, which is a Dickey state, well, I should basically just sweep the paintbrush continuously, but I should take into account the profile of the cavity decay. So this, in principle, is a way of making these kinds of states with in principle, perfect fidelity, even with losses and scattering. What goes down is the success probability if the cavity lifetime is short, right? But it's a heralded scheme that in principle can give very high fidelity. Real world limitations, one needs to compete against things like dark counts of the photodetector, okay? And at the end of the day, there will be some limit that is set by the cavity cooperativity. But not surprisingly, there should be some limit on how macroscopically one can make these states with realistic success probability, with reasonable success probability. But in the limit where one has a very good detector, this is a really promising scheme for making very pure entangled states in a heralded fashion. Okay, so we put in some numbers for kind of our cavity, and actually it's not terribly well optimized for getting light out of the cavity, so if you want to make a state that looks like this, we could hope to do it with sort of modest fidelity. If we can generate a single photon deterministically in the cavity, this looks like deterministically in the cavity, then we can hope to push that fidelity up. And so one of the dreams is to actually sort of combine this idea of having some maybe control atom that allows us to deterministically generate photons in the cavity with a detector that allows for sort of maximizing the fidelity of the state preparation. And this is, so we were excited as a new direction in kind of controlling collective spin states, but also this actually could have applications to controlling states of, for example, mechanical oscillators. This is, and maybe one day raises sort of the question, what else can you do conditioned on photo detection? Is this a new direction of maybe simulating novel interactions conditioned on the light that comes out of the cavity? Okay, so with that, I want to thank my research groups of the highlighted in red are the experimental team on the cavity QED experiment, and we've also benefited from lots of theory collaborations, including with Brian Swingle, who's in the audience. And with that, I will take questions or let you go along.
Over time, we have one question.